this brings me to this discussion of the very early phases in the specification phase. So first of all, we can capture our specifications as text. We should not ignore that plain text is sometimes a very good way of capturing specifications, and that means in one way or the other we have to do our capturing. This can be done in any natural language such as English or Japanese. We can also try to make that a little more formal, but in any way typically we are using text here. Even though we are just using text, we can nevertheless have some support by some kind of design system, some kind of user interface to a computer. There we could be using a tool that is processing machine-readable specifications. It would be nice to have version management so that we can input the new requirements and then possibly backtrack to some earlier requirements in case we realize that the new requirements are leading us into the wrong direction. And also it would be nice to be able to explicitly represent dependencies between different parts of our description. So for example, there might be some text which implies some other text, and that in turn implies some third text. These dependencies would be nice if they were explicit in our design representation. There are commercial systems that are available which support exactly this phase. For example, there is the DOORS system, which right now is a property of IBM, and any interested party can buy this from IBM. Now, I'm not going into the details there because this phase is something that's typically discussed also in software engineering courses, and I'm trying to minimize the overlap with software engineering courses. So as a second method that we can use during the early phases, we have so-called use cases. That means we're describing possible applications of our system under design. Use cases are a very convenient way of making sure that the final system will really implement what the user is interested in. Therefore, the Unified Modeling Language, or UML, which is designed to support especially these early phases, is including use cases. So as an example, let us look at the graphical representation of the different use cases for an answering machine in UML. There we have two persons. We have a user and we have a caller. And then the user expects a certain number of use cases to be supported. So it should be possible to play the next text for an answering machine. It should be possible to erase the last message from an answering machine. It should be possible to erase all messages. It should be possible to turn the answering machine on and off. And for the person calling the answering machine, it should be possible to have a welcome message there, to have a beep, and to have the recording of the voice message that's left by the caller. So as you can see from this example, there is neither a very precisely specified model for the computations in the components in this model, nor is there any precisely specified model of the communication. So intentionally, we keep this at a more informal level. Now again, I'm not going into the details there. Again, the goal is not to have too much overlap with the course on software engineering. Therefore, I'm immediately moving to the third method that we can use for modeling specifications in the very early phases. And this third technique is called sequence chart. Earlier, this technique was also called message sequence charts. In this case, we are adding a little more detail to our specifications. In this case, we are explicitly indicating the exchange of information. In one dimension, typically the vertical dimension, we are denoting time, and the other dimension, typically the horizontal dimension, is reflecting the distribution in space. So if, again, we are referring to that answering machine, we see the caller, we see a phone, and we see the answering machine. And the caller is then typing in numbers to his phone, and his phone is then sending a signal to the answering machine. The answering machine is waiting for some time, and then when the answering machine gets the impression that no human is picking up the phone, the answering machine is simulating a pickup, and it's then sending an announcement, and this announcement is then forwarded to the caller. And also there is this beep, which is forwarded to the caller, and the beep is also sent to the caller. And the caller could then send a message, and the message would be sent to the answering machine. And finally, when the caller is returning the handset, we would signal the end of the call. So in that way, we can describe the different sequences that we have there for the different components that are involved here. We know the sequence of messages that we have there for the phone. We know the sequence of messages for the caller and for the answering machine. We don't have precise timing information there. We just know that certain things happen in the sequence. We know that certain things happen as a consequence of some other things happening first. Now, in order to have a slightly more complex example, I'm using an example that we came up with when we had a European project where we tried to interface some simple sensors with a network over which we wanted to get access to the values that were measured using these simple sensors. So in that case, we have 3 levels of nodes there in our network. Level 1 nodes are the most comprehensive nodes that might store a certain database. Level 2 nodes do have standard internet protocols running on them, and they could represent, for example, laptops. And then we have level 3 nodes, and level 3 nodes are simple nodes. They typically correspond to sensors that do not necessarily run an internet protocol. Then you can have such a situation where, let's say, some simple router is sending a ping signal to some other component there, and then gets some signal back. As a result, some ID gets transmitted there. This ID gets then transmitted to the level 1 node, and the level 1 node then sends a message over the router back to this initial node. And after this setup of the communication, we can have a situation where the sensor is asking for a connect, and this connect signal then gets propagated throughout our system. And in this way, we can represent the sequence of communications that take place in such a system. Now, as an even more complex system, I'm now referring to a real application that may be used to you. And this is an example that I have copied from my dear colleague Lothar Thiele from ETH Zurich. According to this example, we are studying an in-car navigation system. That means we have a car radio with an integrated navigation system. There we are expecting as a user to have some fast response by the system, and this fast response includes all the use cases that we have for the system. In particular, we assume that there are some incoming traffic messages, some TMC signals that should be processed in a timely way, and several applications may be executing concurrently on this car stereo. So one application would be to use the user interface to get information about the route to some destination, and also we would like to get information about the accidents that are somewhere on the road. So the overall system is comprised of several components. In our early model of the overall system, we assume that there is a man-machine interface. We also have a navigation subsystem, which is interfaced to the database where we store some geographical information. And we have, as a subsystem, the radio. which in turn is linked to the antenna and the speakers. Now, let's consider the different use cases. The first use case is a use case in which we would like to decrease or increase the volume of our stereo. So we are turning the wheel there, and as a response of that, we would like to have a different volume of the music, and also we would like to have some visual feedback there. So in this context, we are requesting to have feedback that is sufficiently fast so that we get the impression that we're actually having an impact there on the stereo. So therefore, the requirement according to this specification includes a visual response of less than 200 milliseconds. So it shouldn't take too long until we see something changing there on the display. Also, the audio feedback should be faster. That means if we turn this wheel there, there should be some more or less immediate reaction of the stereo, and we require this reaction to take less than 50 milliseconds. Now, in our sequence chart model of this use case, we have the different entities. We have the user, we have the man-machine interface, and we have the radio. And we can annotate this sequence chart with certain additional information. This actually goes a little bit beyond the standard information that can be included in a sequence chart, but usually there are extensions that allow you to indicate additional information. So for example, we can indicate that there are at most 32 events of this type per second. That means we can't change the volume too frequently. 32 changes per second is already quite a lot. So we see this as an additional annotation there that provides some hints to the system and that gives some hints to the system regarding the overall performance that's required. Also, we might include information on the amount of communication, on the number of bytes that need to be transmitted from one entity to the next entity. This also has an impact on the performance that we require for the communication there. And also, to make this not too complicated, we assume that there are some available execution time estimates. So we assume that we know that we need a certain number of instructions to be executed. If we press some key, adjusting the volume also needs a certain number of instructions to be executed. And to keep this rather simple, we assume that there is a constant execution time for these instructions so that we also have a good estimate on the total execution time for each of these actions. Now, furthermore, as an annotation, we have to add the constraint on the maximum delay. So, for example, we can add as an annotation the constraint on the delay between us changing that little wheel there of the car stereo and the feedback which we are getting as the user. So this is a way in which we can use the use cases for that in which we can use the sequence charts for the first use case. Now we also have to look at another use case. As a second use case, we could try to look up a certain destination address. We would like to see some friend of ours, but we forgot the address. So in that case, we would like to fetch the address from the database. Again, we have a specified maximum delay there. We assume that the reaction doesn't have to be really immediate, but the delay also shouldn't be too large so that we get the impression that the system is actually working for us. Again, we can capture that use case as a sequence chart. So in this case, we see the user. We see that there may be inputs to the system, not that frequent anymore because we cannot have 32 checks for a particular address per second. We will do this less frequently. And also in this diagram, we are indicating the size of the messages. So in this way, we can represent the second use case. And we can do this for a third use case, we can assume that there is an incoming signal from the antenna. The signal from the antenna might transmit some information about some accident. This might refer, the message might refer to some geographical position, and it might be useful to first check the database, what's available about that particular location before we send anything to the display of the stereo. Since the user doesn't really know at what time this radio signal is coming in, we can allow for a larger delay there. Again, we can capture this use case in a sequence chart, and we can see that there is a message which gets sent from the radio station to our radio, and from there to the navigation system, and from there to the man-machine interface, and from there we have some implicit communication with the user, and again we will annotate this message sequence chart with the allowed delay. There are more applications of these sequence charts. For example, we can try to describe the traffic on the tracks of a rail system using these sequence charts. In this case, we will see this later on, the time typically reflects real time, and the different locations over here, they are typically corresponding to stations. So in this case, we are describing the fast train traffic that exists between Cologne, Aachen, Amsterdam, Brussels, and Paris. And we are describing a situation where a train is staying for some time at Cologne, so that's due to the vertical segment that we see over there. And then the train is going to Aachen. It stays there for a short amount of time, continues on to Brussels, stays there for a short amount of time, then goes to Paris, stays there for a somewhat longer period of time, then goes back to Brussels, and from there goes back to Aachen, and from there goes back to Cologne. Now there might be a second train which goes from Amsterdam to Brussels and which arrives more or less at the same time also at Brussels. Now, looking at this particular example, we see a particular weakness for this type of diagram. Because in practice, what happens is that there are short trains that go from Cologne to Brussels, and there are also short trains that go from Amsterdam to Brussels, and the two are connected at Brussels and then continue on to Paris as long trains. Now, in this diagram, it's not possible to figure out whether these two trains meet at Brussels by coincidence or whether some synchronization is really needed there at Brussels. So you don't really know what type of communication, what type of synchronization you would have there at Brussels, because that's not explicit in these diagrams. So therefore, as a disadvantage, we see that there is no distinction between some accidental overlap and really needed synchronization. Yeah, that's a certain weakness there. We can go a little further into the same direction by now really looking at the way that the schedules of rail systems are represented. They are typically represented as so-called time-distance diagrams. And in the time-distance diagram, in the vertical direction, we now really have real time. So we see real time written down there in the vertical dimension. And we might even have a situation where in the horizontal dimension, we really have real distances. In this case, we only see some symbolic distances. So in this diagram, we see a good set of trains that are running somewhere in Switzerland. I got this diagram from another group there at ETH Zurich. There you see that there is, for example, a train leaving a station called GW, and from there it runs to some other station called SP, stays there for some time, and from there continues on to some other station, stays there for some time, and then somehow we don't see it anymore. In such a diagram, the slope that we see here for the lines, they represent in a way the speed of the trains. The more vertical these lines are, the slower the trains are. In particular, if they are staying at the stations, we really have a vertical line there. Really, horizontal lines are not possible because that would violate the principle of maximum speed. So no train can be faster than the speed of light. In this way, we can really represent the traffic on a rail system very conveniently. And this is a representation which is actually used in practice. Now, in order to play a little bit around with such diagrams, we have designed a little animation unit, and with little animation unit, it is actually possible to play around. So therefore, I'd like to start this little animation unit, which is also accessible to you. Right now, I have to start this from here. It's an animation unit for time-distance diagrams. It's written in Java. That's why it takes some time to start up. It's still starting up. So this is this little animation over here. We can see the different schedules represented at the top. And down here we see the different tracks. Now we can add, for example, additional trains if we would like to add a new train. Let's say we want to add a so-called new timetable. We select a certain color for the new timetable. We want this to start, let's say, at Cologne at a particular time. And we are selecting the time over here. Let's say it's time 85. There we are selecting the train. If we scroll a little further down, we see, come on, scroll down. We see that there is a train starting at Cologne at that time. And then we can add additional destinations there. Like in this case, we can, let's say, I think it works like that. So we have what is called the breakpoint. In this case, we have a station at which the train is waiting for some time, and then we can have that train continuing on to Brussels, and maybe after some time it goes back to Aachen. Now we can run the system. We can select the speed. I'm slowing the speed down because this helps us to really see what's going on. And then we can see the trains running. So over here in the lower half of the diagram, we can see the trains going. They are going pretty slow right now. I can scroll this a little further up. So there we see where we are. What we see in the lower half is exactly the traffic that is represented in the schedule in the upper half. And after some time, you will see that the new train that we added is also using the tracks that are available for this traffic. So let's wait for a few seconds until this new train is then actually becoming visible. Just a few seconds again. Now it should arrive somewhere. Starts at Cologne, there it is. It's at Aachen. Went from Cologne to Aachen pretty fast. Now it's going to Brussels. And at some time it should go back from Brussels to Aachen. So that's a little simulation tool that you can use to play a little bit around with these time-distance diagrams. Okay, let's go back to the slides. So there are these sequence charts. They are included in UML. However, in UML, in these sequence charts in UML, we don't have real-time information. We just have some ordering between certain events. If we would really like to describe real-time, we have to use a different diagram type in UML. and such a different diagram type is actually available in UML. This diagram type is called the timing diagram, and I would like to describe an example that you're familiar with in order to introduce these timing diagrams. So in these timing diagrams, we now have time running in the horizontal dimension. In practice, we would have to indicate the real physical time there, so we have to be a little more precise than what's possible in this limited space here in the slide. And here we assume that we describe the situation that you actually are a witness of for this course. We have a professor, we have a recording assistant, and the two are in different states. So for example, the professor typically is working on some other duty. He never has free time in this diagram. He always is working on some duty. And the same is true of the recording assistant, by the way. So normally the professor is working on some other duty. Then he starts the preparation of the next lecture, and then he does the actual teaching, which is just a small fragment of the overall time. And after that, he's very happy that this is over, and he works on some other duty. And after some time, he realizes that the next lecture is approaching. He works on the preparation, then does the actual lecture, and then starts to work on some other duty. Like I said, he never really has free time. So, and it's the same with the recording assistant. The recording assistant also has some other duty. And then when it's about time for the next lecture, that the recording assistant has to work on the next recording. After the lecture, he has to work on the editing so that everything becomes available on YouTube. Fortunately, there is some time left for some other duty. There is no time left for some non-professional activities, so there's always some duty. And then it's a time for the next recording. So in this way, you see that we can indicate specific actions together with a real time there, and in order to do this in UML, we really need a different diagram type. It's not possible with sequence charts, but timing diagrams are available in UML as well. So talking about sequence charts, we also have to mention other problems that exist with sequence charts. During very early phases of sequence charts or the use of message sequence charts, we are interpreting these sequence charts frequently as something that could happen. So if you would like to capture a certain situation, we are describing that something could happen. However, in this case, we would like to describe that something actually should happen. This is something that we really expect. Any deviation from this would be a mistake. Now, how do we do this in sequence charts? Well, actually, it's a common problem that we see for sequence charts because during a more detailed specification phase, we would like to use the same mechanism to describe something that must happen. And in one way or the other, we would like to distinguish between the two, something that could happen and something that must happen. And with standard sequence charts, that's not possible. So therefore, there have been a set of colleagues, actually they are mentioned down here in this little footnote. There are Werner Damm and David Harrell, who proposed the introduction of so-called live sequence charts, and live sequence charts are defined so that we overcome this limitation of sequence charts. Now I'd like to describe the extensions that we see for live sequence charts, and again I'm referring to a situation that you're used to as well. The first extension for live sequence charts is that we are able to introduce so-called precharts. These precharts are describing a necessary condition that must be met if the main chart really applies. And in this case, I'm using as an instance, as an example, also something that you know from this course. We assume that we have a professor there, we have a microphone, we have a camera, we have a teaching assistant. It's the same as a recording assistant when we have an actual recorder. Now, before we start the recording, we assume that the professor steps in front of the camera and the camera transmits certain signals to the recorder, and then the TA is checking whether these signals are actually visible on the recorder, and this means that the video signals are actually expected there at the teaching assistant. And we do the same with checking the audio, so the professor is expected to say a few words into the microphone. This signal gets transmitted to the recorder, and from there hopefully also to the teaching assistant. And if the teaching assistant has observed that video and audio are actually arriving at him, he will press the recording button and tell the professor, you can start your lecture right now. Now this is a necessary precondition. If this is not met, we will not start the lecture. Yeah? So that means we will exit that diagram in case that precondition is not met. Now during the actual lecture, there will be audio and video signals that get propagated from the professor to the microphone and to the camera, and from there to the recorder, and frankly, I'm not sure how much the TA cares about what arrives in between. Yeah? So that's the situation. That's an example of how we can describe the use of Precharts. Now in general, there are several ways in which we can introduce this distinction between something that must happen and something that may happen. In this extension, we are using solid lines to indicate something that's mandatory, and we are using dashed lines to indicate something that's provisional, something that could happen. So if we use solid lines for the chart, this means that all runs of the system must satisfy that chart. If we have a chart that's drawn with dashed lines, that means there is at least one run where the system satisfies what's described there in the chart. Then for the location, if we are using locations with solid lines, then we know that we must be moving beyond the current time, beyond the current location. If we are using, for the same purpose, dashed lines, that means there is one instance where we actually move beyond the current location or time. And it's similar for messages. If a message is sent, it will be received, whereas if we are using dashed lines here, the receipt of the message is not guaranteed. And for the conditions, if we are using solid lines there, the condition must be met, otherwise we abort. In the other case, if the condition is not met, we exit the subchart. So that means in this case I have used dashed lines. That means if the condition is not met, we will exit that chart and work on something else. So these were some extensions that are very useful. Let's summarize the use of sequence charts by looking at reasons of using these sequence charts, and let's also look at the reasons against these sequence charts. I think these sequence charts are very appropriate for visualizing schedules. We have seen that the variant called time distance charts is used for representing schedules and transportation systems for decades. It's very useful there. Also, this way of describing systems is standardized. There is a ITU recommendation for message sequence charts. And also the semantics is defined, so if it's not immediately obvious what you mean by a certain graphical notation, you can look at the standard, and hopefully the standard will clarify the meaning of a certain graphical chart there. However, there are also arguments against the sequence charts. These sequence charts are just describing one case. They are not describing timing tolerances. And also, it's not immediately obvious what does a sequence chart specification mean. Does it describe all behaviors of a system, or does it just describe a sample of behaviors? So that's a problem that we have with standard sequence charts. Any question with respect to that? No question.